Good afternoon, and welcome to the annual Keeling lecture here at the University of Illinois. It's a proud tradition. It kicks off our Earth Week events here. Earth Week, there are a number of speakers invited over the course of the week, today, tomorrow, and I would just give a brief plug for a talk that is being given on Friday afternoon by Jonathan Overpeck, another climatologist who is Dean of the School of Sustainability at the University of Michigan. He'll be giving a talk on new drought projections for the Southwest and the Great Lakes area at 3:30 p.m. on Friday, just over there in the Spurlock Museum auditorium. So if you have, I'm sure I'm speaking to an interested audience here, so please make sure to put on your calendar Jonathan Overpeck for Friday afternoon, 3:30 at the Spurlock auditorium. But first things first, today and the annual Keeling lecture, when I scouted out for potential candidates to give this prestigious endowed lecture, our guest, Professor Kerry Emanuel from MIT, was at the top of everyone's list, and we're so glad that he was able to come to be with us today. I'd like to thank our sponsors for the event, the School of Chemical Sciences, the School for Earth, Society and Environment, the Department of Chemistry, the Department of Atmospheric Sciences, and the Institute for Sustainability, Energy and the Environment. Now there will be, after the lecture, there will be a period for question and answer, and then I'd invite you to join us for a reception with some food and wine where we can continue on the conversation. Now I'd like to hand it over to Jeff Trapp, the Chair of the Atmospheric Sciences Department, to formally introduce our speaker.
Hi, good afternoon. I'm Jeff Trapp, head and professor in the Department of Atmospheric Sciences, and I have the pleasure of introducing our speaker for today. But before doing so, I've been asked to give a few words about the history of this event. This event is named for Charles David Keeling, a 1948 University of Illinois graduate from the Department of Chemistry. He determined how to make extremely precise measurements of atmospheric carbon dioxide. These measurements clearly indicated that the atmospheric concentrations were increasing, leading to the recognition that human activities have a significant impact on the Earth's climate system. After receiving his PhD in chemistry from Northwestern University in 1954, Keeling spent most of his career at Scripps until his death in 2005. As the first to confirm the accumulation of atmospheric CO2, he produced a data set that's now known as the Keeling curve, and his measurements are renowned as the single most important environmental data set taken in the 20th century. Each year, the School of Chemical Sciences, the School of Earth, Society and the Environment, the Department of Chemistry, the Department of Atmospheric Sciences, and the Institute for Sustainability, Energy and Environment come together to sponsor a lecture to honor Keeling's legacy. I'll turn my page here. This institute, IC for short, was created to bring together the best minds at the University of Illinois to tackle grand challenges faced by society. It leverages the enormous academic strengths here at Illinois to conduct interdisciplinary, actionable research addressing grand challenges in energy and the environment, to train the next generation of scientists and leaders, and finally, to make campus a national model of sustainability. I see the schools and the departments are all pleased to welcome Professor Kerry Emanuel as the Keeling lecturer. Dr. Emanuel is the Cecil and Ida Green Professor of Atmospheric Science at MIT, where he has been on the faculty since 1981. Much of Dr. Emanuel's research focuses on the meteorology of the tropics and climate change. His specialty is hurricane physics, and he has contributed significantly to our understanding of how long-term climate change might affect hurricane activity. His interests also include the dynamics of cumulus convection, including severe cumulus convection, which is the topic of today's lecture. Dr. Emanuel is the author or co-author of more than 200 peer-reviewed scientific articles and has authored 3 books, including Divine Wind, The History and Science of Hurricanes, published by Oxford University Press, and also what we know about climate change published by the MIT Press. He received an SB degree in Earth and Planetary Sciences and then a PhD in Meteorology, both from MIT. After completing his doctorate, he joined the faculty of the Atmospheric Sciences at UCLA, where he remained for 3 years with a brief hiatus filming tornadoes in Oklahoma and Texas. In 1981, he joined the faculty of the Department of Meteorology at MIT and was promoted to full professor in 1987 in what has since become the Department of Earth, Atmospheric, and Planetary Sciences, or EAPS. In 1989, he assumed directorship of the EAPS Center for Meteorology and Physical Oceanography, a position he held until 1997. Subsequently, Dr. Emanuel chaired the EAPS program in Atmospheric Oceans and Climate from 2009 to 2012. He's the co-founder and serves as co-director of the MIT Lorenz Center, a climate think tank which fosters creative approaches to learning how climate works. We're excited to have him here this evening to deliver the 2019 Keeling lecture entitled Severe Thunderstorms and Climate. Please join me in welcoming Dr. Kerry Emanuel.
Well, thank you very much, Jeff and Jillian. It's a great pleasure to be here today and also a privilege. I've certainly enjoyed my conversations with some of you earlier today. And as Jeff mentioned, my topic today is the connection between severe weather and climate. And this is a topic that is motivated in part by Jeff's own work, very seminal work in this area. I know that we're having some problems with the projector, but I can't see it. So if you can't see it, someone has to wave to me. It's on now, right? So this is a subject I think that needs a lot more work. There's been only a little bit on it, and I started to get interested in it by coming actually from the climate standpoint. And we want to know fundamental questions like what really does control the level of activity of severe thunderstorms on the planet in a given climate, in the very most fundamental level. Why don't we have more of it? Why don't we have less of it? And so we have to look at this in the context of the fact that climate is changing. And so as you, I'm sure, are aware, records of temperature on the planet going back to the end of the 19th century show fairly unequivocally that global mean temperature is going up. That's the red curve you see in this diagram. There's, of course, a lot of fluctuations due to natural effects and other climate forcing, such as volcanoes. But the blue curve, of which the part that's post-1958 is what Jeff referred to as the Keeling curve. It came out of Charles David Keeling, who graduated from this department. The blue curve is a measure of the carbon dioxide content of the atmosphere. This relationship between temperature and carbon dioxide was predicted at the end of the 19th century by Svante Arrhenius, a giant in the field, a chemist. There's a lot behind it. There's a lot to say about it, but I'm not going to be talking principally about that today. But a subject that I'm fairly sure if Keeling, if we were around today, would be interested in, which is among many other aspects of climate change, how would we expect this to affect the incidence of severe thunderstorms around here and elsewhere on the planet? In the course of doing this research, I sort of thought, well, when I started this was not going to be terribly interesting, and I came at it with a slightly negative point of view, that this was just a matter of tallying things up. But I didn't, as often happens when you get into research, it becomes more interesting. And you sort of stumble on things you didn't expect at all. And it was kind of an exciting journey for me, and I hope some of that excitement comes across for you. So I want to begin by saying that I think it's helpful when talking about convection to start at the beginning and to talk about global convection, not just severe convection, but the much more ordinary and common sorts of convection. And I like to think that, and I think there's reason to believe that there are two fundamentally different kinds of moist convection on the planet. There's what I refer to as quasi-equilibrium convection. And what this is a fancy term, but what it means is that convection is always very close to being in equilibrium with what forces it. A classic everyday example is a boiling pot of water, right? You have convection going on, you have bubbles and things, and you know from experience that what controls the intensity of that is how much heat you're putting into the burner, right? If you turn up the heat suddenly, If it's already boiling, it's going to boil harder, and it doesn't take long for it to boil harder. It's about as fast as the coils warm up. If, on the other hand, you put a thermometer in the water, what's it going to read? 100 degrees C. And no matter how high you turn up the burner, it's always going to be 100 degrees C. So if you want to know how hard it's boiling, you don't look at the thermometer. It's not going to tell you. It'll tell you whether it's boiling, but not how hard it's boiling. You need to measure how much heat's going into the burner. Well, most convection in the world, particularly over tropical oceans, works that way. The intensity, the amount of convection you have is pretty close to how hard you're forcing it, where the forcing is the flux of heat from the ocean surface and also the radiation of heat in the form of infrared radiation to space. So in this concept, convection consumes available energy at the rate that large-scale processes produce it, just like in boiling water. Most convection in the tropics over water, and most middle latitude convection in the summertime is of this nature, with the proviso that a diurnal cycle, a day, is a little bit too fast for quasi-equilibrium. Convection can't keep up, which is why it peaks more like 5 in the afternoon rather than at local time, noon. But with that aside, it's pretty close to being in equilibrium. It's generally benign because it's common. We're used to it. It doesn't cause us much problems. In fact, in many parts of the world, it's the source of most badly needed rainfall. So it's responsible for a significant fraction of that rainfall. Then you have the other kind, and I call that stored energy convection. That may not be the best phrase for it, but that's when you don't have an analogy in boiling water to that. It may be a stick of dynamite is a good analogy. You actually have a lot of available energy that sits behind a chemical barrier in that case, and a physical or thermal barrier in the convection place. It builds up, and then somebody lights a fuse, and bang, it goes off, all right? That is, in undergraduate meteorology programs, commonly the first kind of convection that's taught to students, and sometimes they make the mistake, at least my students do, of thinking that's how all convection works. But it's actually the less common globally kind of convection. So it's relatively rare. It may not be so rare around here, but on a global basis, it's pretty rare. And it's responsible for most of the problems that convection cause. Tornadoes, large hailstorms, flash floods, sometimes strong straight line winds. And so they're really quite different kinds of convection, and I think it's important to make that distinction. So if you go down to the tropics, this is a photograph taken in the Seychelles Islands near the equator in the Indian Ocean. Doesn't get much more tropical than that. This is what a tropical skyscape looks like. It's always filled with clouds. It's virtually always convecting. There's showers around anywhere. You could easily fly an airplane through those clouds and not notice it very much. You might notice it a little bit, but it wouldn't be dangerous to do that. And there's a whole spectrum of clouds. These are relatively shallow. You can see that they're raining. There's a rainbow. That's a sure sign that there's rain. In the background, in the right-hand side of the background, you can see that there's very deep convective clouds there. Now, this is a little bit more for the meteorologists in the crowd, but if you look at tropical soundings, and I spend a lot of my life doing that, by the standards of mid-latitudes, they're kind of boring. So what's on this chart, this is a thermodynamic diagram. It has temperature, although the temperature is not on the horizontal axis. Isotherms are actually the sloping black lines that go up to the right. Its vertical axis is pressure in equal increments of the log of the pressure. So it's approximately linear in altitude, but not quite. And the red, the bright red curve you see there is temperature as a function of height measured by a weather balloon going up through the atmosphere. And the green line is the dew point temperature measured by that same balloon. Now, there's a slight difference between this and an ordinary in that I'm actually plotting something called the density temperature. It's gone, huh? Okay, well, is it back? All right. Sometimes all I have to do is wiggle a little bit, and we'll see how far I get. But thank you for waving, because I don't know what's going on. The density temperature has been slightly corrected for moisture content, so that it actually reflects more precisely the density of the air. Now, we can use a diagram like this to do various sort of hypothetical exercises to see whether air coming from near the surface, if it went up by a process we call an adiabatic process, would be buoyant if it's lifted up. So I'm going to show you, just to make matters slightly confusing, and also to illustrate that we don't really know how to do this, 3 curves. The red dashed line is something called a pseudo-adiabat. So it assumes that when the air goes up, as soon as the water condenses, some mysterious demon removes it, all the condensed water. And that makes the air lighter because condensed water weighs down the air, contributes to its effective density or density temperature. And you can see that that air, which has been lifted from near the surface, if it's lifted up, it's slightly warmer than the environment through which it's being lifted. So that would have some positive buoyancy, and we would say it's an unstable sounding by that measure. And that's what's mostly used in exercises to do this. The blue dots are the opposite extreme. It's also lifted adiabatically, but this time we keep all the condensed water in the air. We don't let any of it fall out. So it's the other side of the spectrum. We don't even let any of it freeze, and it should when it gets high enough and cold enough. But you notice those blue dots, those dark blue dots, lie very, very close to the sounding. And this turns out to be a shockingly systematic aspect of tropical soundings, that they're almost exactly neutral to a reversible adiabatic process, and I have no idea why. It shouldn't be. There's all kinds of reasons why it shouldn't do that, but it does do that. So there's an enduring mystery. If you tell me the temperature and moisture at around the 950 millibar pressure level, in the tropics, I can, with great accuracy, predict what the whole rest of the tropospheric temperature or density temperature will be. That's remarkable. Now, the light blue dots are a third process in which it's also pseudo-adiabatic, like the red dashed line, but I'm allowing air to be entrained from the environment by a certain way of doing entrainment, which we don't know is correct, but we've tried all kinds of different ways of doing that. And you can get pretty close to the reversible adiabatic, but not quite by doing that. So it predicts the sounding pretty well, except for the upper parts of the sounding doesn't do so well. This is one sounding, but this is systematic over others. The point is here, the overriding point, is that we believe that whatever we're seeing here, the tropical atmosphere is kind of neutral to this process. It's like sticking the thermometer in the boiling water. You don't know where it's boiling, let's say, and you stick it in, and it says 100 degrees C. It's a pretty good bet it's boiling. Well, this is the equivalent. It's critical. It's right at the critical point, and we see that all the time in the tropics. Now, the stored energy convection is different. It looks different. It behaves differently. You don't even have to be an atmospheric scientist to look up the sky. When you see that, it doesn't look like the convection I showed you over the Indian Ocean. It looks very different, okay? It looks to some people like the end of the world. For some people, it is the end of the world. You know, you have skies like this. A lot of people in this crowd, I happen to notice this picture was hanging in the corridors of the atmospheric science group. So this has 2 tornadoes in it. These are the kinds of storms that produce violent weather. And if we look at the statistics in the United States, alas, these storms, tornadoes, kill on average about 60 people a year. 1,200 tornadoes on average, and they injure 1,500 and cause about $400 million in damage. These kinds of storms, unlike the tropical convection, also produce hail, which does even more damage than tornadoes, $1 billion a year, to crops mostly and some to property. Okay, so these are destructive. And you know, it's interesting, I gave this talk in France before I gave it here. And the French were very unimpressed by these US statistics, and you could see them beginning to wink off when I showed them this. So I got them, because I really got their attention when I showed them something that's much worse than this, even worse. 8 million bottles worth of champagne grapes wiped out by a hailstorm, okay? Actually, France has a big problem with hail, and they know it. In fact, arguably, the precipitating cause of the French Revolution was a pair of hailstorms that crossed through France in the year before the Revolution and wiped out the wheat crop, leading to massive hunger and unrest. All right, so these are very different beasts, okay? And I'm not suggesting that there isn't a continuum between the two types, but largely they're separate. And if you look at atmospheric soundings that you see around the time of such events, they look very different. So this is the same kind of diagram I showed you before. But this is a sounding not from, I neglected to say, the first one was from an island deep in the Pacific tropics. This one is from Norman, Oklahoma. And you can see that it's the temperature decreases rapidly, but there's a little temperature inversion there around 850 millibars. And then the temperature elapse rate is much steeper above that. And so if I plot these three hypothetical processes, it qualitatively doesn't matter, whatever process you choose. An air parcel going up, if you look very closely at this, it's actually negatively buoyant when it gets up to around 800 millibars. And for that reason, the air from the boundary layer doesn't really want to ascend spontaneously. It's trapped, if you will. But if you can get it to go much above that, it's not only positively buoyant, it's very positively buoyant. And if it were actually to go up in an updraft, it would be a very powerful updraft, all right? Until the air got up to somewhere over 200 millibars, when you finally go into the stratosphere, does it finally become negatively buoyant. So the soundings look very different. And we have many ways of quantifying those. One is a property called and I'm sorry if I'm boring the atmospheric science students a little bit here, but hold on. One is a quantity that we just call CAPE, the convective available potential energy. And it is a measure of how much updraft speed you could generate if you know the buoyancy of the sample. And it literally, on a diagram like the diagram I just showed you, which I have a cartoon of here, is proportional to the area, physical area between the adiabat that you lift the parcel up and the environmental temperature. So the greater the difference, the greater this CAPE. And the updraft speed is proportional to the square root of this quantity. Also, we have a related quantity, which I should have put on this slide, called the convective inhibition, which is the negative area, we call it, that's down at the bottom of the sounding where the lifted parcel is colder than its environment. And that's a measure of how hard it is to get the boundary layer to convect. So that Oklahoma sounding I just showed you, if you look at that one, I thought I had that on here. This is the Norman, sorry, I'm going backwards, that's why I don't have it on here. It has 6,900 joules per kilogram of CAPE. If it were all converted into an updraft speed, that would be going at 110 meters per second. Now, of course, it's never that efficient, but we do see very, very strong updrafts in these storms. Order 60, 70 meters per second, I think, have been seen in radar and so forth. Whereas the tropical convection, it's a few meters per second, 3 or 4 meters per second. That's why you can fly an airplane through it. You do not want to fly an airplane through the second kind of convection, okay? If you see the pilot doing that, please tell him to turn around. It's not a good idea. And it's that kind of updraft speed which is necessary to produce the severe phenomena I alluded to. For example, to get large hailstones, you need strong updrafts. So let's look at the climatology of hail here in the US. This is a climatology from 2006 to 2014. And you can see that the largest hail, the largest size hailstorms and the most frequent hail is in the plain states of the US. Extending somewhat into the Midwest as well. There's almost no hail west of the Front Range of the Rockies. It's very rare. And so one of the things we would like to know from a point of view of the climate is why do we have this particular distribution? What's dictating? What about the climate system favors hailstorms, severe convection there and not in California? Or where I live in New England, where we do sometimes have hail, but it's relatively uncommon. If we look at, again, for the United States, the monthly or seasonal distribution of hail, the red bars are for 2-inch to 3-inch hail, the orange for more than 3 inches, and the yellow for more than 4 inches. But anyway, you can see that the month of May is the peak month. April is the second most frequent month there. When I was walking over here, I saw there were some thunderstorms north of here. I hope they weren't producing hail, but they could have been, I suppose. And if you look at and so this is another question for climatologists: why? What's so special about April and May? And this is the hour of the day, okay, in local time. And you can see that the peak occurrence of hail is in the late afternoon, about this time of the day, a little bit later maybe. Well, about this time of the day. And now we're looking at a distribution of hailstorms, annual significant hail distribution from 1955 to 2004. And it looks like there might be an increasing trend, but I don't think there's much confidence that's really true, simply because the practice of reporting hail, measuring it, observing it, has changed a lot over time. And so I don't know. I'd have to ask Jeff whether he believes this curve. It's out there, but we would like to know if there is a trend. And I don't think there's much confidence in a chart like this. If we look at tornadoes, it's broadly a similar distribution. They are creatures, as most people know if they watch The Wizard of Oz, of the Plain States, and to some extent the Midwest. And so what we have learned from studying these storms with models and in nature is that you need, usually, you can find exceptions, to get them, there's several conditions that are met. You need to have large values of the stored energy, and you need to have large changes of the background wind with altitude, a condition we call wind shear, particularly at low levels. And what I want to address today really is just the first point, okay? It's a big enough question in itself. I'm not going to be looking at the climatology of shear, but you should keep in mind it's equally important. I'm just going to ask, what is it about the climate system that produces large CAPE in some places at some times, and why do we see the values we see? You know, why is it a few thousand joules per kilogram and not 20,000 or not 200 or some other number? What is it about the climate system that dictates that? Now, if you go to textbooks, particularly dated ones like my own, you'll see diagrams like this that purport to be an explanation for why you see large CAPE in the plain states of the US. And the explanation is that you have air that comes from Mexico or the desert Southwest, which has been superheated at its base, but with very little moisture put into it. So it's formed over high deserts. It has very steep temperature profiles because of that. They're dry adiabatic approximately through a large layer. And that air, that's the light gray arrow, gets advected, gets moved by the background winds over moist, very moist, but much cooler air coming northward from the Gulf of Mexico. And it's that combination that supposedly produces these large values of CAPE. That's what a lot of people believe. It's certainly what I believed until recently. And qualitatively, this is not wrong. Quantitatively, it turns out not to be the biggest show in town most of the time. That's the surprise for me. So there's nothing more fun than kicking your own past work, but that's what I'm going to do here. Now, part of what led me on to this also was a very peculiar chart that was produced years ago by Ted Fujita, who was a master of the climatology of tornadoes. And I could never figure out why he produced this chart. Some of you may have seen it. It's showing a distribution of world tornadoes, the black dots on this diagram, and agricultural areas, green. I said, well, what has that got to do with anything? You know, what is it? It's this canonical picture of the tornado behind a silo, and he's got that in mind, so he thinks there's a connection between tornadoes and farms. And I look at that chart, and I always laugh and say, what was he trying to tell us? And I'm not laughing anymore at this, because I think there's actually something to it. And that's going to be the bulk of what I'm going to try to get across to you atmospheric people. This may be a little bit new to you. Certainly it was new to me. And we're going to come back later and re-examine this chart. I just want you to look at it now. And I want to re-emphasize another thing we have to explain about severe weather, that it is primarily a creature of the late afternoon and early evening. Wherever you look, local time, you don't find very many severe thunderstorms at 4 o'clock in the morning. Sometimes, but rarely, all right? They're mostly in the afternoon. Same thing with hail, as I showed you before. So I would say the key questions from a point of view of a climate person is what determines the geographical distribution of these storms? Why do they peak in the late afternoon to early evening? And most importantly, why are these peak values in the range that they're observed and not some other number? And will that number, this comes back to Charles David Keeling, is that number changing, and will it change because of climate change? Because that would have implications. It doesn't tell us everything we need to know, but it's a start, okay? So how could those change? How might those values change with climate? So I'm going to now sort of leap forward and tell you about a kind of a radical hypothesis that it's too early to say whether this is right, but naturally I'm going to supply some supporting information, otherwise I wouldn't be telling you this, that the Large Cape isn't really so much a matter of dry air flowing over moist air. It's more a matter of dry air flowing over moist soil. And that's the new angle to this. I'm going to try to convince you that the degree of soil moisture is really a key ingredient in building up large values of CAPE, okay? And some of this is published, and I've given you a reference here if you want to look at it. Vince Agard, who's really the author of a lot of what I'm talking about now, was a graduate student of mine. He's now working for a firm in Los Angeles that does agricultural forecasting for Thailand, so he's off in a very different direction. So here's how to think about it. Let's start out with desert air, air that's formed over hot, dry deserts. And let's just simplify things. There's no moisture in it at all. That's, of course, an extreme thing, but we're trying to look at things through a simple lens. So if I plot temperature versus altitude in such an air mass, it's going to be a straight line. We do see this, by the way, over deserts all the time. And the temperature is falling at about 1 degree per 100 meters, 1 degree centigrade per 100 meters. The dry adiabatic lapse rate, ho-hum, that's pretty boring. But the next thing we're going to do is we're going to take this air mass and we're going to pick it up and put it down over a wet soil. And we're going to let the wind blow a little bit to cause a turbulent boundary layer. And we're going to ask what happens then. What does it look like? What does the sounding look like afterwards? Am I still good? Do I still have a picture up there? Okay. So the red dashed line shows you what happens to the temperature. The boundary layer, which is that little thin area at the bottom of the picture, a new boundary layer begins to develop, and it's much cooler because of evaporation of water from the surface. And I'm going to now first consider a wet soil, but not a very wet soil. We're going to consider the limit of a fairly dry but still wet soil. The water evaporation is going to cool the air, and you're going to get a much cooler boundary layer. Now, the green is the dew point temperature, which was off the chart because I assumed there was no water. But then, of course, you're evaporating water from the soil. You're going to build up some moisture in this boundary layer, all right? So that boundary layer is cold, and it's a bit wetter than it was before. Now, if we took a sample of air in this boundary layer and lifted it up by an adiabatic process, because it's still pretty dry, it goes up pretty far along this dry adiabat before water begins to condense where that black arrow is, and then it goes up a moist adiabat. And at this particular stage, eventually the moist adiabat would become as warm as the dry adiabat, but not warmer than that. So you have 0 CAPE, okay? But now we're going to let the sun come up. We're going to turn on the sun. As far as a thought experiment, we'll just turn it on instantly. We're not going to let it rise slowly. We'll just turn it on like it was a bright light. And we're going to heat the soil. We're going to start with that state. What's going to happen is because the soil is not terribly wet, a lot of the heating will go into actually heating the air. Some of it will go into moistening the air. So the boundary layer, the new boundary layer, that second profile on the right, rapidly becomes deeper. It's becoming hotter, it grows, it entrains the dry air from above it. And even though there's moisture coming from the soil, the air in the boundary layer dries out, because as the boundary layer grows, it's engulfing this very dry air above it. And so if you now lift air along the dashed line to the right, it goes up a dry bed. It's not nearly as cold as it was before, and now the water begins to condense at an even higher altitude, and eventually the moist adiabat crosses over the initial profile, and you get some cape, but not very much. Now we're going to repeat that exercise, except with a very wet soil. By the way, it's not the same thing as the ocean. This won't happen over the ocean because the ocean's enormous thermal reservoir. It's very hard to change its temperature. So this is sort of peculiar to very moist soil. Now, what happens is that initial boundary layer that's formed mechanically is much wetter because the soil is much wetter. So the atmosphere is actually cooler in this case than with the dry soil, but it's also a lot wetter. So the dew point temperature is not very different from the actual temperature in the boundary layer. If you lift a parcel, it won't go up very far before water begins to condense, and it will go up this moist adiabat. And you're going to have more cape, but also more convective inhibition. Now you turn on the sun, and what you find in this case is that the boundary layer does not get deeper nearly as fast because a lot of the sunlight is now going into evaporating water. So the boundary layer only grows slowly, so it's not entraining a lot of dry air from above by growth. So maybe the dew point temperature falls a little bit or may even go up a bit because of evaporation from the soil. That's a bit indeterminate. But whatever happens, you're going to have a lot more cape, but compared to the dry soil, still a lot more convective inhibition than you had. And this is just a qualitative way of illustrating the importance of soil moisture in the diurnal growth of the boundary layer and the associated convective energy in this. Now, this is a brief, for the atmospheric scientists, and I'll try to hold this down for the rest of you, a very brief sort of attempt to make this quantitative. And it's simple to do, it turns out, if you've done boundary layer physics. So we're going to have to define a bunch of quantities. The dry static energy, it's the heat capacity times temperature plus gravity times altitude. It's conserved in air that is not being heated and doesn't have phase change of water. There's the moist static energy, which is the same thing, but it has the latent heat of vaporization times the concentration of water. That's conserved even under a moist process with condensation and evaporation. The boundary layer depth, H, its time rate of change, which is called the entrainment velocity. It's how the boundary layer grows by entraining stable air from above it, or turbulence-free air from above it. The surface sensible heat flux and the surface latent heat flux. So those are the actors in our play, okay, as these variables, so the actors. And then we have a bunch of equations that govern how they evolve with time, and I don't want to bore the non-atmospheric scientists too much with this, but the first is conservation of dry static energy. It just says that it'll change if you put sensible heat in at the surface, or if you entrain air with different dry static energy. D naught is the dry static energy of the initial air mass and above the boundary layer. It's constant with height along a dry adiabat. This is one for the growth of the moist static energy. And above the boundary layer, because there's no moisture, the moist and dry static energy are the same. That's why you have a D naught in this equation. But the surface fluxes is the net surface plus latent, which is equivalent to the sunlight, because we're considering the soil to have no heat capacity, which is pretty much true. And then we have Doug Lilly's famous formulation for entrainment that says the entrainment is the work done against buoyancy, and that's proportional to some fraction of the surface sensible heat flux, A. A is usually around 0.2, and we're going to use that. And then aerodynamic formulas for the surface sensible flux. And the latent heat flux, we're going to put an artificial coefficient alpha in front of, and that's my cheap, dirty trick for controlling the soil moisture. It's 0 when it's dry, and it's 1 when it's wet, and it's in between. It's not a true soil moisture, but it's the variable I'm going to change here. And then this, the sum of the latent and sensible is the net flux, which appears in the conservation of moist static energy. We have our definition of entrainment velocity. And the initial moist static energy, or I should say at all times, is of the soil is related to the dry static energy just by the Clausius-Clapeyron equation. And the moist, we're taking as an initial condition that the moist static energy is equal to the initial dry static energy of the free troposphere in this initial boundary layer that we're starting with. And the dry static energy of the initial boundary layers determines that the air at the top of the initial boundary layer is just saturated. That's our initial condition. And we non-dimensionalize the variables. And again, I don't want to bore you with too much of it. I just want you to know it exists. If you're interested, I can lead you to the appropriate reference. You can boil it down to one predictive equation. It's nonlinear for the height of the mixed layer. And then a bunch of diagnostic relationships to go along with that. So it's a very, very simple system you can solve in 1 second or less on your laptop. It's not a big deal model, okay? So before showing you graphical solutions, I want to look at things which I think are very interesting, which is the long time behavior, which you can actually figure out from the equation themselves. You let a lot of time go. We're going to let the sun rise. We're not initially going to let it set. We're just going to keep it on and see what happens, okay? If the total surface flux is greater than some critical value that depends on the temperature of the soil, it turns out that the CAPE reaches a maximum at some particular amount of time that's elapsed since you started the problem, and then it falls to zero eventually. And it falls to zero because the effect of entraining dry air as the boundary layer grows overwhelms the input of energy from the surface fluxes, and it actually starts to go back down again and then goes to zero. And then you're finished, okay? There's no point in going any further. But if this condition is not met, it turns out CAPE still reaches a peak value at a particular time, but it doesn't go back to zero. It goes back to some value, some definite value, which you can figure out what it is. It's sort of given here. The normalized dry static energy goes to 1, as does the surface. The air temperature in the boundary layer becomes the same as the surface temperature. The moist static energy goes to a definite number. It depends on the parameters. And the boundary layer starts to grow linearly in time. The boundary layer top never settles down, but instead of blowing up, as it does in the first case, it just goes linearly with time. And we can also solve for the CAPE in this problem. In a problem like this, it's really just the difference between the moist and dry static energies times really a function of how deep the troposphere is. So it turns out that in that first the second limit, which I call the warm limit for reasons that will become important, when the boundary layer growth becomes linear in time, the CAPE itself asymptotes to a particular value, which is given. This is the only equation I'm going to put any weight on in this talk, all right? So if you don't like equations, just hold on for a minute. And the term on the right, the log of the boundary layer temperature over the anvil temperature, is just kind of a measure of the depth of the troposphere. But the two important terms are in brackets. The first is proportional to the saturation water content of the soil, which is just a function of its temperature. And it's Clausius-Clapeyron. It goes up very quickly with temperature. And it's a positive contribution to CAPE. Oddly enough, the surface fluxes, in their role as entrainers, in fostering entrainment's a negative influence, but it's weighted by the inverse of the surface wind, V, okay, in the denominator. So the stronger the winds, the less negative that term is. So one recipe for getting high CAPE in this regime is to have a hot soil, the hotter the better, or the more CAPE, and to have high winds, which will make the second term. And, I think I put this on here, CAPE rises exponentially with surface temperature. It increases with surface wind speed. It increases with soil moisture, that alpha parameter. You see, the higher that is, and if it's 0, you're in trouble. Long before it gets to 0, you're not going to have any CAPE. If it's large enough, you will, and if it's 1, that's the maximum amount you can have. And also, oddly enough, this sounds counterintuitive, for a given surface temperature, the CAPE declines with absorbed solar radiation, this F net. And that's again because the radiation is what's forcing the boundary layer to grow and become more dilute. It's all much more interesting than I thought it would be and somewhat not intuitive. I mean, you really have to sit down and figure this out. So let's look at this graphically. This is the cold regime, and I don't know how well you can see that. Is the projector holding up so far? Okay. This is the growth of the depth of the boundary layer with time. These are non-dimensional numbers, so the numbers don't mean anything unless you know what the non-dimensionalization is. But what happens is it grows, and then it blows up, and then you're finished. You can't do that. Okay, the boundary layer is basically gotten as deep as it can get, or as hot as it can get. And if you look at the dry static energy, the temperature of the boundary layer, it goes up and sort of asymptotes until you have to stop it. The moist static energy goes up and then it goes down. And so the surface temperature also rises and then at the end falls. And this is the CAPE curve. So it goes up, 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 and then suddenly it plummets down. And this is when the boundary layer gets deeper really fast and is training all this dry air. So it doesn't do it. Now we go to the other regime. And this is really a different regime when you pass some critical point. This is the boundary layer depth. It grows, it grows. It looks like it's going to blow up, but no, it settles down to a much more orderly, linear increase in time. And it's linear for the rest of time. You don't have to stop the model. The dry static energy and the moist static energy both asymptote to constant values at long time, in spite of the fact the boundary layer is growing. And the surface temperature becomes equal to the air temperature at the surface. So you shut off the sensible heat flux, which is interesting. And CAPE, as I said, goes up. It reaches a peak value. I've put these in dimensional terms for you, by the way, the CAPE. And then it asymptotes to a constant. Now, it turns out if it's very warm, the behavior is somewhat the same, but the CAPE doesn't peak and fall. It just asymptotes to a constant value. Now, again, in this warm regime, the amount of CAPE you can get and the amount of inhibition both go up very quickly with soil moisture and soil temperature. So this is just showing the CAPE curves versus time for different values of the soil temperature. Now, I've put this in dimensional terms, going from 290 in the case of the little blue curve at the lower left, up to 310 in the case of the green curve. So you can see how quickly those values increase. If we put the peak values versus initial surface temperature, remember in the plains here, you know, in the summer, in the spring, it may be 295 or 298. It's not going to be 305 or 310, but I always like to push models as far as they'll go, see what happens. And this is CAPE plotted on a log scale. I mean, those are actual CAPE values, but they're spaced linearly in the log of the quantity. And these are for particular values of soil moisture that you in heating that you see there. Okay, that's fair enough. So the answer seems to be that if you want to build up large CAPE, the recipe is to take a deep, dry adiabatic layer. We've assumed it's infinitely deep. That's what you do in the beginning. You make simple assumptions. Put it over a wet soil, and the hotter the soil, the stronger the wind blows, and the moister the soil, the more CAPE you're going to get. Now, what happens if we let the sun set? Because it actually changes the problem in some interesting ways. And the way we're going to let that happen, here's the curves I just showed you of CAPE versus time when we don't let the sun set. The sun setting, we're going to do is we're going to shut the sun off at some time. So the sun instantly turns on and instantly turns off. Of course, you could make it fancier if you wanted, but it's not going to change things qualitatively. So we're going to turn it off at where that black line is. Now you can see for the colder temperatures, it doesn't matter. You were already finished before you got to sunset. CAPE went up and then it went back down. So if the soil is dry enough or cold enough, you're going to get your peak CAPE sometime in the day, and then by the time the sun sets, it's all over anyway. All right, sunset's almost doesn't matter. But at the higher temperatures, it does matter. You interrupt this growth right in the middle of it, and that's what you have. You're not going to grow the boundary layer anymore or put more moisture into it after the sun sets, or not an appreciable amount. So you make that the limiting value and you graph that peak CAPE, regardless of the regime, versus temperature, taking into account realistic sunset, it still goes up rapidly, but not quite as catastrophically as before. It begins to level off at high temperature. And what that means is a prediction here, that as you raise the temperature, the peak CAPE occurs later and later and later and later in the day until it occurs right at sunset. Okay? So if you're going to look for a signal for climate change, unfortunately, you have to hold everything else constant, which it almost never is. One prediction is that the peak severe storm should occur a little bit later in the afternoon. Whether you can detect that with observations, I don't know, but it's a prediction anyway. This is showing those same curves, same curve, but for different values of this alpha, the soil moisture, with red being dry. If it's 0, nothing happens at all, by the way. So it's a big difference between whether alpha is 0 or 0.1. And as you make it wetter and wetter up to 1, CAPE grows faster, but ultimately doesn't get to larger values at high temperature. But in that mid-range of temperature, it's very sensitive to soil moisture. Higher surface winds, this is just turning up the surface wind speed from 5 meters per second to 25, going from blue to yellow. Big effect of the wind. It's changing the partition between latent and sensible flux. Now, finally, I hope I'm not running too far out of time, but this is the end of it. Let's see whether there's any support for this in actual observations. So what Vince did, and this has not been published yet, alas, is to look at 8 cases of severe weather outbreaks. And what you see on the left, if you can see it, it's pretty tiny, are 8 maps showing severe storm reports in those dots, various kinds, hails, tornado. Don't want to get too much into that. And then the right-hand charts that correspond to that, although the alignment isn't perfect, sorry about that, are graphs of values of CAPE, okay, corresponding to about the times when those storms, just before those storms developed. And you can see that there's a pretty good correspondence geographically. As you expect, the severe weather develops pretty well where the CAPE is large. Okay, there's nothing particularly new about that finding, but what Vince did was to take the places where the severe weather is reported and go backwards in time to see where did the air come from. So for those 8 cases, he chose a lot of initial points near the severe weather and traced the flow back at 700 millibars, about 3 kilometers above the ground. That's the red line, so they're going back in time. And the blue is near the surface, going back in time. So that upper left chart shows just what I had in my textbook. The lower level air is coming from the Gulf of Mexico, and the high level air is coming from the desert southwest. And you see that in a lot of these diagrams, but not all of them, all right? So, oh, well, that's pretty nice. There are some really, like that lowermost left chart doesn't look like that at all. The upper level flow is coming from the high plains and not from the desert southwest. We can find other cases where it's coming from the East Coast, believe it or not, rarely. So it's not ubiquitous. But now if we choose some of those low-level blue trajectories and follow the CAPE values along with time, this is what you see. So this is going backwards in time. That chart at the left, and it pertains to that second graph down on the right, shows the evolution with CAPE over 45 hours, that's all, up to the time of the severe weather outbreak. And what you see is that most of the big increase in CAPE occurred in the last 8 to 10 hours, i.e. in the day before that. That's the sun rising, okay? And then the real shocker was this graph. If you look at all these cases, and you look at what made the CAPE value so large, you looked at this differential advection, the thing I thought was true when I put that graph in the textbook. That is the red bar at the bottom. It's almost nothing. It's positive, but it's not very big. Almost all of it came from heating the boundary layer, all right? That was the big deal. Now, of course, the large-scale environment has to be there to allow this to happen. You have to have the dry air aloft and so forth. So I'm suggesting to you that the soil moisture and the way the boundary layer grows in the daytime is really important in many of these cases. And at about the time we were doing this, they started to show us satellite-derived soil moisture maps. And I would argue on the basis that this is not climatology. This is a snapshot in April, about this time of year, 4 years ago. It's a snapshot, and I would argue that the recipe for building up large Cape is to have dry soils upwind of moist soils, big moisture gradients. So what you're looking for is big west to east gradients, mostly in middle latitudes. In the tropics, that you may see those, but there's no wind shear, or not much wind shear, so it's not going to do much in the tropics. But so let's look at where that happens. Well, here, the plain states is an obvious candidate, the big gradients of soil moisture from west to east. The Pampas region of Argentina, and by the way, when we did this, we didn't know you guys were running an experiment down there. I just heard about that today. There are lots of severe storms in that region. This is the wrong time of year to be showing you the moisture chart. These are in October and November, which is their spring, not April. The region between India and Bangladesh is another region that sometimes has large gradients from the deserts of the Pakistan and so forth to the very wet, swampy Bangladesh. And Bangladesh indeed does have some pretty severe weather. Southeastern Australia is another place. Europe, some years, but not other years. If you look at different years, you can see this in Europe as well. Central China. And I don't know, frankly, much about the climatology of severe storms in China, but that would be another place to look. And so maybe Ted Fujita, all those years ago, wasn't crazy when he drew this map. You want to look at wet soil regions, farmlands, and there's the intriguing idea that not only is this changing in time because of climate change, but it may be changing in time simply because of agriculture, because agriculture does change the water availability of the soil. Have we, without realizing it, having nothing to do with traditional global warming, changed the climatology of hail and tornadoes over the periods in which we instituted large-scale agriculture? That's a question I don't know the answer to, but there's some evidence that that's true. This is showing from a paper that Jeff Trapp was involved in that if you look at climate models, you do see increases in the number of days with the appropriate environments for severe thunderstorm, which is not just Cape, but it includes that as a factor. They're growing. So I've gone a little over time. Let me wrap up. So I'm being a little bit provocative here because I scared myself, and I'm not sure what's going on anymore. When I was doing this, where large Cape seems to occur when you take deep, dry adiabatic layers that are formed over deserts and advect them over moist soils. That may give you a connection to agriculture. Peak values of Cape scale approximately with the difference between wet and dry bulb temperatures, and that increases exponentially with surface temperature. So yeah, we expect to see more Cape, but more convective inhibition, all the things being equal, if you don't change the soil moisture and wind shear and things like that, as the climate warms. So that would sort of suggest that on the whole, you would see fewer storms because there's more inhibition, but the ones that do occur might be more violent. But don't take that as hard truth. This is the beginning of the process. Imposing the diurnal cycle limits the growth of peak Cape with surface temperature. You expect as the climate warms, the peak to occur later until it's occurring at sunset. Then it can't go further. It increases with wind speed and soil moisture, and this is something I didn't say, but because soil moisture has a memory, if you know what it is in March, you might be able to start to say something about the probability of having severe weather in the coming severe weather season. So it offers a tantalizing prospect. We might be able to start doing seasonal forecasts of the probability of severe weather. That's a bit of an esoteric point, but soil moisture could yield multiple equilibria. If it's wet, you get convection, the soil stays wet. If it's dry, you don't, and the soil stays dry. And that's something that needs to be looked into as well. Thank you very much. Yep.
So if you're running models and most of our data comes from differential convection, and yet it should actually come from soil moisture, which may not be well visualized in models,
Yeah.
you could be well off the mark early on.
That's right, and I think this is an obvious area for research, right? If we look at forecast models and we look at cases where they got it right and so forth, we could do the same kind of diagnostic that Vince did from the reanalysis data. Where is the moisture coming from? Is it coming differential advection or coming from the soil? And there's so many things you could do with this. That's why I say this is just the beginning.
But that would also actually get into then your differences in the different kinds of convection for your severe weather system, for example, your more isolated convection that's perhaps earlier in the season versus say your MCS type convection that comes a bit later in the season. So I'm just kind of wondering, like, have you thought? I mean, I know it's like again, this is very early work, but thinking about how that lines up with the climatology of the different kinds of severe convection that we see.
Yeah. I mean, so one obvious question is why the seasonal cycle? I even said at the beginning that was important, but then I didn't say, why I thought this was going on. So that one possibility is that, there's another ingredient I didn't talk about, which is shear. And around here, it's a lot less in the summer. So you may have the other ingredients and you don't have that. And the differential advection would be much weaker just because the flow is weaker. But this is, as I say, there's a lot more work to be done on this. Yeah.
Very interesting talk. I think according to folks at the Storm Prediction Center, if you look observationally at severe weather outbreaks, most of them are predated by a few to several days of moisture return out of the deep tropics.
Right.
And if you contrast that with something like, say, I think 12 days ago, you had a 980 low over Kansas in April.
Yeah.
And there were no tornadoes reported. And if you look at the back trajectory, well, cold front cleared the Gulf a couple days before, and you had air coming out of the continental polar high out of the southeast, brief excursion over the Gulf and coming out. And you had some convection near the triple point, and the entire dry line was capped. So I'm curious as to what your time scale is for the soil moisture to work here, because it's got to be faster than, or it's got to be slower than a couple days to substitute for a true NTR.
Yeah. So, the soil moisture clearly has longer time scales than a few days. There's no question about that, for the most part. I mean, obviously there are exceptions. You have dry soil, there's a lot of rain, and but everything else has to line up too, right? You have to have this advection of very deep, dry air over the moist soil. It can be over moist air too, but the really important thing is to have it happen over moist soil. So how long does that take? And the soil has to be warm as well. So you have to have all those things. It's not just wet soil. So, I mean, I think, as I say, this is begging for an observational analysis that we haven't done except for those back trajectories.
Right, I think it would be interesting to look at, for example, bust cases as well, to see where that air was coming from, and I think there'll be a difference.
Yep.
So I was wondering if you could walk me through the argument that it's only the soil moisture. Because, so both, for example, in the plains and in Argentina, you have the low-level jet
Yeah.
And it wasn't 100% clear to me how we could rule out the moisture that's being affected.
Yeah, we didn't. I mean, we never said from first principles we should rule that out. What we did was to do these back trajectories, and we said how much of the accumulation of CAPE along the trajectory was advective versus an input from the soil. We just did that. Now, this is reanalysis data, you could argue. If there were small differences, I'd say the reanalysis data isn't, good enough, but there were huge differences. So it all had to do in this, and we only looked at 8 cases, but in each one of those cases, it was the way the boundary layer grew. Now, one thing that's important is the soil temperature, but think about that for a minute. What's actually determining the soil temperature, right? It's complicated. It's not just the amount of sunlight coming in, it's the air temperature. If you have very cold air over the soil is going to be cold. And it's not just the amount of sunlight going in. So remember, the soil temperature was an independent variable from the sunlight. So, whatever determines the soil temperature is important. It's not just the soil moisture. But without it, if it's very dry soil, there's a prediction, no matter what else is going on, you're not going to get anything to happen. One other thing I should have said is you could generate a lot of CAPE by this mechanism, and if it's not released, you can advect that CAPE, if you will, elsewhere for a while. So of course you can have nocturnal storms. The air doesn't get released, and then it goes up over a warm front, and the cap goes away, it's released. So there's a time delay on this, can be a time delay on its release, as always. Could be, if it's large enough scale, yeah. So, people say, well, can we alter the climatology of tornadoes by irrigating or not irrigating? Go sell that to the farmers. But what I like to look at is upbeat. If you could irrigate all of northern Mexico and the desert Southwest, you could get rid of the dry adiabatic layers, maybe. That, in principle, you could do something. It's probably infeasible, but yeah. Thank you. Yeah.